The efficiency of commercial aircraft improves on average between 1 and 1.5% per year. In 2013, inside a wind tunnel in Virginia, a scale model proved it was possible to cut fuel consumption in half. Those are two numbers. One of them describes the pace at which the aviation industry has been advancing for decades. The other describes what happened when someone decided to stop advancing along the same path and start over. 10 years after that test, the aircraft that proved those numbers should have changed everything. Instead, it was quietly buried, and then the story took a turn no one expected. Look at any airport in the world. The planes parked at the gates look different from each other. Different sizes, different liveries, bigger or smaller engines. But if you strip away the paint, the engines, and the details, the structure underneath is the same. A tube, two wings, engines hanging underneath or attached to the tail. This shape has a name in engineering, tube and wing, and it has dominated commercial aviation since the Boeing first took off in the 50s. The 707, the 727, the 737, the 757, the A320, the A330, entire generations of aircraft designed by different teams in different decades for different markets, and all following the same fundamental architecture. Each new generation brought more efficient engines, lighter materials, aerodynamic tweaks, but the structure underneath it all never changed. Engineers knew this, and for a long time, the gains from those tweaks were enough. A new engine saved 15% on fuel. A composite material reduced fuselage weight by 20%. Winglets cut another 2 or 3% of drag. Added together, those gains were real and financially justifiable. The problem is that each successive generation produced smaller gains. When you've already optimized the engine, already swapped aluminum for carbon fiber, and already redesigned the wing profile 3 times, the room left for improvement shrinks. The curve of diminishing returns begins to flatten. And at some point, the question changes. It stops being, how do we make this aircraft better, and becomes, is this aircraft still the right answer? In 2008, NASA decided to ask exactly that question, with funding. The agency created the N+3 program. The acronym stood for Next Generation Plus 3, meaning 3 generations beyond the aircraft in service at that time. The plus 3 was deliberate. N+1 meant the next generation, perhaps a decade away. N+2 was 2 generations. N+3 was the most distant horizon the agency considered useful for planning, aircraft that would enter service around 2035. And the goal wasn't to redesign the 737 or make the A320 a little lighter. The goal was to imagine what would come after everything the industry already knew, to start with a blank sheet. The targets reflected that ambition: roughly 70% less fuel consumption compared to the reference generation, approximately 75% fewer nitrogen oxide emissions, and a drastic reduction in noise around airports. The reference aircraft against which everything would be measured was the 737-800, the workhorse of American domestic aviation, flying missions of 180 passengers over 3,000 nautical miles. 70% less fuel than a 737. To put that in perspective, if the industry continued at its pace of 1 to 1.5% gains per year, it would take between 40 and 70 years to reach that number through incremental evolution. NASA was asking engineering teams to find a way to compress half a century of progress into a single conceptual leap. And here's a detail that almost no coverage of this program explains properly. NASA didn't build anything. It did what it does in nearly all of its aeronautics research programs. It funded independent teams to compete for the best concept. Among the teams selected were MIT, Aurora Flight Sciences, a Virginia-based company specializing in experimental aircraft and autonomous systems, and Pratt & Whitney, which contributed propulsion studies. The money was public, the research was open, and the mandate was clear: forget what exists. If you could start from zero, what would the ideal aircraft for 2035 look like? What came out of that mandate didn't look like an aircraft, at least not in the sense that anyone would recognize looking through a terminal window. The team led by MIT designed a fuselage that, seen from the front, looked like 2 cylinders glued side by side, something like the number 8 lying on its side. This shape was given the name double bubble, and the entire aircraft was christened the D8. The exact origin of the name depends on who you ask. The 8 may simply be the configuration number within the family of designs Drella developed. The first instinct when seeing the D8 is to think the engineers were trying to be different, but the strange shape wasn't the objective, it was a consequence. Every design decision in the D8 existed to solve a specific efficiency problem. If the most efficient solution had looked like a conventional aircraft, the D8 would have looked like a conventional aircraft. It looked different because the right answer was different. The fuselage of a conventional aircraft is a cylinder. It's good for pressurization, good for serial manufacturing, good for maintenance. But aerodynamically, it's passive. A cylinder cuts through the air. It doesn't help support it. All the lift comes from the wings, and the heavier the aircraft, the larger the wings need to be, which increases the weight, which demands more lift, which demands larger wings. It's a self-feeding cycle. The double bubble fuselage broke that cycle. By flattening and widening the fuselage, creating that cross-section shaped like a figure 8 on its side, the MIT engineers made the fuselage itself generate lift. The fuselage stopped being merely a container for passengers and cargo, it became an active aerodynamic surface. In the program studies, the D8's fuselage produced roughly 20% of the aircraft's total lift, 20% that previously came exclusively from the wings. This allowed for smaller, lighter wings with less drag, and smaller wings meant less structural weight, consequently less fuel needed to carry the aircraft itself. And the D8 went further. The wings had a span of about 36 meters, comparable to the 737, but with reduced sweep, a smaller angle that decreased drag, and allowed for a thinner, lighter wing. The tail was a pie tail structure, two vertical surfaces connected by a horizontal one that took advantage of the elevated engine position to shield propulsor noise from the ground. But the D8's most impressive innovation wasn't in the fuselage, it was in the engines, or more precisely in where they sat and what they did with the air. On any commercial aircraft you know, the engines are positioned to receive clean air, air that hasn't yet touched the aircraft's surface. This exists for a reason. The air flowing along the fuselage creates a thin layer of decelerated, turbulent air called the boundary layer. This air is messy. It has different velocities at different points. Engineers spent entire decades avoiding this air because it reduces fan efficiency and increases blade wear. The D8 did the opposite. It positioned the engines at the rear of the fuselage, exactly where the boundary layer is thickest. Instead of avoiding the turbulent air, the D8 swallowed it on purpose. The concept is called boundary layer ingestion, BLI. The logic behind BLI is counterintuitive but elegant. When a conventional engine generates thrust, it accelerates clean air that was already moving fast. That works, but it wastes energy. When the D8's engine ingests the decelerated air from the boundary layer, it's re-energizing air that would otherwise be wasted as drag. The engine does the same thing, accelerate air, but from a more efficient starting point. The result is that the aircraft needs less total energy to stay in the air.
All of this was theory until 2013. That year, the team from MIT and Aurora brought two 1/11 scale models, one with engines in the BLI configuration, the other with conventional engines, to the 14 by 22-foot wind tunnel at NASA's Langley Research Center in Virginia. The comparison was direct. Same model, same simulated mission, same conditions. The only difference was the engine position and whether or not the boundary layer was being ingested. The measured result was a power benefit of roughly 8.6% from boundary layer ingestion alone. 8.6% might seem small in isolation, but that was only the BLI gain. Combined with the lift generated by the fuselage, the smaller wings, the lower structural weights, and the optimized engines, the program's projections showed a progression, roughly 25 to 30% fuel savings with the technology available at the time, approximately 33% from the new aerodynamic configuration alone, and close to 50% when combined with technologies anticipated for the following decade. The N+3's ultimate target, 70%, was a long-term horizon, but the path to get there ran through the D8. The numbers worked, the physics worked, the wind tunnel confirmed the simulations. But between a scale model in a wind tunnel and a certified aircraft carrying 180 passengers lies a chasm that few concepts in the history of aeronautics have managed to cross. BLI required the engine's fan to operate with extremely distorted air, flows arriving from different angles at different velocities simultaneously. No existing commercial fan in the world had been designed for that. It would require developing a completely new fan, with blade geometry capable of tolerating this distortion without losing efficiency and without breaking. And the new fan means a new certification program, certification that costs billions of dollars and years of testing. There was also noise. Under certain conditions, the interaction between the distorted boundary layer and the fan blades generated acoustic frequencies that could increase noise instead of reducing it, exactly the opposite of one of the N+3 program's goals. And there was risk. The double bubble fuselage was not a cylinder. The structural joint between the two lobes, the point where the two bubbles meet, needed to withstand pressurization loads in geometries the industry had never certified. The manufacturing methods existed in theory. In practice, no fuselage factory in the world was set up to produce them. Even so, NASA kept investing. In 2016, the agency announced a $2.9 million contract with Aurora Flight Sciences to develop a demonstrator-scale version of the D-8 within the new Aviation Horizons program. The idea was to turn the concept into an X-plane, the class of experimental prototypes that had been pushing American aviation since the 40s. The announcement seemed like a sign that the D-8 was advancing towards something concrete, and then, a year later, came a communique of completely different nature. On October 5, 2017, Boeing announced its intention to acquire Aurora Flight Sciences. On November 8, the acquisition was complete. Aurora, with its more than 550 employees, its research centers in Cambridge and Switzerland, its factories in West Virginia and Mississippi, began operating as a subsidiary of Boeing Engineering, Test and Technology. The official statement talked about autonomous systems, unmanned vehicles, electric propulsion. The word D-8 did not appear. In the months that followed, public output on the concept ceased. The researchers who had worked on the D-8 went on to academic careers.
It's possible that Boeing absorbed elements of the D-8 into future programs. The BLI technology, the Langley test data, the non-cylindrical fuselage. All of it now belongs to Boeing, the same Boeing that participated in the N+3 program with its own concept, Sugar. Sugar evolved, secured funding, and in 2023 became the X-66, a billion-dollar experimental demonstrator. The wing assembly was handled by Aurora, the same Aurora that had built the D-8. In April 2025, Boeing paused the X-66. It needed the engineers to certify the 777X and the last variants of the 737 MAX, the very same tube and wing aircraft that the N+3 program was created to replace. Meanwhile, in the Mojave Desert, a California startup called Jet Zero is building a full-scale aircraft where fuselage and wings merge into a single surface, engines at the rear. A promise of 50% less fuel. United Airlines signed a letter of intent for up to 200 aircraft. Alaska Airlines invested. United, Japan Airlines came on board too. The first full-scale flight is expected by the end of 2027. The question NASA asked in 2008 didn't disappear. It just changed address.